Hello everyone, welcome to another edition of our AI virtual classes brought to you by Data Science Nigeria. This edition is titled Deep Learning 101 for students and professionals, and it's going to be facilitated by one of our top experts, Dr. Stephen G. Odaibo. You can reach out to Dr. Stephen Odaibo on Twitter at @Odaibo, or you can reach out to us at Data Science Nigeria on Data Science at Data Science NIG. Before we start the class, let us share some information with you for you to get to know more about what we do at Data Science Nigeria and how you can be part of it. Data Science Nigeria is the largest AI learning community and solution delivery network in Africa. Our vision is to build 1 million African AI talents in 10 years. In 2019, Data Science Nigeria won the Matai Impact Award at Deep Learning in Daba for impacting hundreds of thousands of Africans with AI knowledge, online, offline, face-to-face, content development, and also facilitating job placement for a lot of young Africans. We also run the biggest free AI learning platform on the continent across campuses, cities, online, offline, project-based, and also content development. So these are pictures of our AI Everyday classes. The AI Everyday classes is one of our initiatives to ensure that AI knowledge is well democratized across various locations, Lagos, Abuja, almost everywhere across Nigeria. These classes are being held every year for 6 weeks. These are pictures from those that have participated in our AI Everyday classes across cities. These are pictures from our AI Everyday at our AI Hub in Yaba. We also run the largest artificial intelligence bootcamp in Africa. This bootcamp we select over 200 smartest young people across various locations in Nigeria to converge and get trained on AI knowledge and also to build their skills in the area of data science and machine learning. These trainings or bootcamps are facilitated by top experts around the world every year, and this is something every young person or AI enthusiast look forward to every year. These are pictures from our AI Everyday classes with one of our international speakers facilitating one of the classes. The AI Club is currently on 17 universities and 23 cities. We are trying to establish more and more AI clubs on more campuses before the end of the year, so that we can reach out to more people in order to build our vision of reaching 1 million AI talents in the next 10 years. We launched the first artificial intelligence book for primary and secondary schools in November 2019. This book is the first of its kind, and it is a book where the basic concept of AI is taught to children in primary and secondary schools grade 4 to 8. This book was written by our founder, Dr. Olubayo Adekombi. The book has secured multiple global endorsements, and local state sales have started thanks to the support of everyone who have promoted it on their social media pages and status form, because it has created more awareness and more people get to know about this book. The book is available across several e-commerce channels. It is available on Jumia. It is available on Amazon Kindle, Amazon Paperback, Apple iBook, Google Play. You can also do bulk orders for this book. You can call the numbers on your screen, or you can simply send an email to aibook@datasciencenigeria.ai, and someone will get back to you very quickly on that transaction. We also help professionals to grow the skills of the future. This is very important for us because as we are supporting the community, we also want to carry the industry along. We have bespoke corporate trainings for organizations, and we also run professional trainings for anyone that is just ready to learn about AI and build their professional career. There are ongoing professional trainings going on online. We have the business and data analytics training that is currently going on, and also data visualization with Microsoft Power BI. This is also another very important class that is going on. You can subscribe to any of these classes. It's going to be delivered online because of the current situation of COVID until things are better for us to go back to our normal physical channels where we deliver trainings. So I would encourage you to subscribe to any of these trainings. If you're a beginner in data science, the business and data analytics program is a very important one. And if you want to learn how to use data to tell stories, the data visualization with Microsoft Power BI is a very important class also. Do not miss out on our Microsoft Azure Professional Certification Training Program. It starts in June 2020. You can call our business or training manager, Sheung, on 0814-00-88800. Let us quickly listen to testimonials of participants in our past professional trainings and let them share some of their experiences with all of us on what their experience looked like when they were at Data Science Nigeria.
Okay, so I chose data science because, it's the future.
The vision of DSN, I identify with it. It's something I can relate with. The vision of wanting to create a hub for data scientists in West Africa. It's something that is highly needed.
Okay, so far so good. It has been a wonderful one. I was able to learn the use of data to interpret data, to predict the future, definitely.
My big take home is probably sentiment analysis and then the use of big ML.
Today we did data visualization, dealt extensively with Power BI. There's a whole lot I can do with it. Things that we've been trying to analyze, I can now visualize it and it will make more sense to my audience.
Big ML majorly, it has been my own major takeaway, and the lectures were so broken down such that anybody can understand it.
So what Sheung told me is lesser than what I even experienced there. The facilitators, they took us like children. It was like a dummy taking the course.
Tell everybody I come in contact with, especially young people in school right now, jobs as we know it will no longer exist. So you should get trained, in one of the technical skills. It could be data science, machine learning, artificial intelligence. That is the future.
So for me, DSN, the vision, is something that every forward-looking Nigerian should identify with.
And let us meet our speaker very quickly. Our speaker today, once again, is Dr. Stephen G. Odaibo. Dr. Stephen Odaibo will be facilitating the topic Deep Learning 101 for students and professionals. Dr. Stephen Odaibo has been a past speaker at our AI for Professionals program in 2018. He was also a guest speaker at our AI for Researchers with Innovation and Research Unit at University of Lagos. He was also a past speaker at our AI Plus Club in schools in 2019, reaching out to young talents in secondary school and inspiring them to become the next generation of AI champions. It was the keynote speaker at our AI Summit in 2019. This is a program where we gather industry professionals, government, students, and everyone coming together to chart a course on how to use AI for socio-economic development. This program was held in 2019, and Dr. Stephen Odaibo was the keynote speaker for this program. Dr. Stephen Odaibo has also been a speaker and teacher at our AI Bootcamp in 2019, was actively involved, and he took several classes at the AI Bootcamp, which was one of the best sessions for all the students in 2019. Dr. Stephen Odaibo is a very esteemed advisory board member of Data Science Nigeria. And let me just read his corporate profile for you to get to know more about him. Dr. Stephen Odaibo is the only ophthalmologist in the world with advanced degree in both mathematics and computer science. Dr. Stephen Odaibo is also the founder, CEO, Chief Software Architect / full stack AI engineer at Retina-AI USA. Dr. Stephen Odaibo is a Doctor of Medicine from Duke University, USA, and also the inventor of the Fluid Intelligence app. Join me as I welcome Dr. Stephen Odaibo as he facilitates this class on Deep Learning 101. Please listen and enjoy the rest of this session. Thank you.
All right, ladies and gentlemen, thank you so much for coming to this lecture on deep learning fundamentals. And I'm especially thankful to be a part of this community, Data Science Nigeria, a real vibrant community of scholars and learners. And I'm especially thankful to Dr. Bayo Adekambi, who once again has invited me to give this talk. Before we go into the mechanism, into details of, what deep learning is and how neural networks work, I would like to say a couple of things about my career and about myself. People typically would reach out to me on LinkedIn, with some frequency, asking for career advice and how to do interdisciplinary science and be in one field as well as the other. And I'm typically not able to these days respond to everyone. So a forum like this is ideal because I can speak to more than one person at once. So a little bit about my history is I am a physician, a retina specialist, and also a data scientist who is working in the context of our company, Retina-AI Health, a company that I founded to solve a real-world problem, which in this case is the problem of access to healthcare. So I was really privileged and fortunate, blessed to train as a mathematician and as a computer scientist. I went to graduate school, for both of those things, and then also went to medical school, and subsequently, and I'm currently practicing a physician. Well, I think that without taking too much time before we get into the topic of the day, one thing that is important is focus and commitment, right? If you're going to do something, you kind of have to have the time for it, right? You might be interested. It might seem like it's the next best thing. It might seem like something that everybody's talking about these days. But ultimately, you have to sort of, in a moment of quiet, decide that you are going to budget a significant amount of your time to whatever endeavor it is that you would be engaging in. And what that means is that you are putting certain other things aside. So that's sort of how to get things moving in the right direction. And deep learning is something that's very important. And I think regardless of what your occupation is, or regardless of what your area of business is, it's just the order of the day. And it is very important now to have a good understanding of data, of how to glean insights from data, regardless of, even if you're not going to become a hardcore machine learning programmer, software developer, or researcher, you still need to, in today's business world, have a good visceral sense of how data decision making works and about what data is. So yeah, so you guys are on the right track, and I'm essentially preaching to the choir here. So now that's my motivational speech. Now let's jump in and look at some data, some deep learning. All right. So what is deep learning? So I Googled this. Out of curiosity, I'm like, let's ask Google what it thinks, and boom, this is what I got. A whole variety, a vast array of representations for what deep learning could be. And so we're seeing all sorts of things here. Some of these things look like waterfalls. Most of these look like graphs with beads, musical instruments, abacus, you name it. And so I'm thinking, well, maybe there is something else out there. Maybe this is not the full spectrum. So let's zoom out a little bit and see wow. And so I do that, and there's a vast array of things. Very quickly, you're seeing beautiful patterns that look like embroidery and various colors and representations. And it's obvious at this point that there's not going to be one rigid definition for what deep learning is, right? Clearly, whatever it is accommodates a vast array, a plethora of representations and forms. So in my view, my take is that, deep learning is using deep neural networks to learn, and learn in the machine sense. And notice that deep there is in, it's in quotation marks, because what exactly does that mean? How deep is deep? Would you say a network of 2 layers is deep? Most people would probably say no. But what about 10 layers, right? that is, I would say deep learning, right? You can solve a lot of problems, with a 10-layer network, and no one would look at that and say, no, that's not deep learning. What about 100? Well, if you say 100 is deep, then how about the person who's working with a 1,000,000-layer network? What would they say? So clearly, this is a relative concept. It's a relative term, and it's not essential to the exercise or to this modality of problem solving. So then, what is? Turns out it's the neural network part that's essential. That's the essential, immutable, fundamental property, quantity, if you will. So the question then, and the more important question, I would say, in my view, is what is a neural network? That's a very clearly well-defined thing, and that essentially is what we're going to be looking at today in this lecture. We're going to be looking at understanding what a neural network is in terms of its form, what it represents, and how it works. So this is a prototypical neural network that's what we call densely connected or fully connected layers. It means every node is connected to every other node in a certain direction. In this case, in the forward direction. And ultimately, all that you actually have in your hand, and this is important to see, is that all you actually can hold in your hand, speaking figuratively, is this first layer, which is the data layer. Right? And data essentially turns out to be just a bunch of numbers. It could be anything, right? Data could be a picture. It could be music, right? It could be a sequence of DNA, like the coronavirus, for instance. It could be your own DNA or genome. It could be a movie, a video, you name it. It could come in various forms. It could be text on a Wikipedia corpus in a book. All of those things are data, and all of those things are representable and represented as numbers. And so basically, that's all you have. And the rest of this representation is essentially a code. It's a set of mathematical operations with order. It says, do this, then do that, then do this, then do that. And that's what we're going to be looking at. And we're also going to be looking at why you do that and what you get out of it. Essentially, we know what we're trying to get out of data is we're trying to get information. We're trying to get something that's not obvious. And we're also trying to get something that we can use to make decisions, to make inference, to know something that otherwise would not be obvious. And often we want to be able to do that automatically using a computer. So that's a lot of the goal, when you look at that. And so you have these things called weights, which, again, they're not physical strings or arrows, but instead they are mathematical parameters and with instruction on what to do with the data, and more particularly, how to transform that data. So we take the data and we want to transform that into some form of knowledge, into some form that is more useful to us for knowing and for doing, which is a lot of what the interface is with artificial intelligence, right? And then here you have the output layer, and at the output layer in this prototype, which is a supervised learning prototype, there's a score. So there's always going to be the concept of a penalty or a reward. So basically, there's some measurement that's taken about how useful the transformation is. So you started here, you transformed into this form. Is it what you want? And insofar as it's not yet, you have a way to know that and say, you're this off, you're totally wrong, we got to fix this, or you're right, you did a good job. And that's the whole idea of learning. It's very similar to how humans learn. So this is the modular operation. As I said, this is a scientific, it's a mathematical set of operations that the neural network represents. That graph you see, that's what it is. And so here you have these x1, x2, x3, and x to n being our data. And then you have these weights, and what you do is you multiply each of those weights by the data, right? And when one gets those products, it's a linear combination, and those weights are essentially coefficients, right? And so here you're going to your destination, which is the ith destination, and you're coming from these j locations, and so each one of them in turn is multiplied by the corresponding weight and summed up together. It's called a linear combination. This is a linear process. And then the output of that is then passed in as argument into what's an activation function, which typically is a nonlinear function. And what that does, the role that plays, is that it increases the expressivity. It allows you to do more in terms of your morphing, right? So the whole process is you're morphing this data mathematically into a form that is instructive for you, into a form that, for instance, you can point out and say it's a cat or it's a dog, if it's a classification algorithm. Or like in our case, you can point it out and say, oh, you have such and such a disease condition, we have to treat you in a certain way. Or you don't, and so you're good to go. Come back in a year for another evaluation. So basically, you take the input data and you morph it through a series of steps into a form that's useful. And that output in a multi-layer network serves as input into the next layer. And then it's the exact same process again. So this is the fundamental operation to keep in mind. It's so important that I copied it out here again from another source on the internet. Both of these are cited. And it's the same thing, x1, x2 through xn, and you have these weights, and then you sum them, and sometimes you'll see a B term. It's not essential. It's not fundamental. It's a bias, which is also a learnable parameter or another weight. That's then added on, and then you throw that in as argument into some activation function, in this case denoted by f, and you get an output. So this is the fundamental operation that's done. And that process and everything I just said can be thought about in two parts, right? You can look at a neural network and say, I'm looking at its structure and its form. And you can think of that as anatomy. What are the different parts of it? What is the input here? These are the input nodes or input data. And then these connecting arrows, as we just mentioned, are weights. And when you do the linear combination there, you get, you pass that argument into activation functions, which are nonlinear functions. And ultimately, you have a score function, which is also referred to as a loss function or as an objective function at the end. Here is just a matrix. So that's the structural representation, which, of course, is not structure in the sense of something you can touch, feel, like strings and the like, but instead these are mathematical instructions. And then you can look at another part of it as the dynamics of a neural network. And you can think of that as physiology or function. The function in the sense of it coming into being, into a useful form or entity. And for that, we look at the process of training, the network, whereby these things called weights or these W's, they're numbers. Everything is a number, right? The data is a number. These are numbers, and what we get out of it is a number, and numbers are going to move around. Certain numbers are not moving, like your input data is not moving, right? But then you are transforming that data into a form that's useful, and so something is changing. Just like when you want to learn something, like you want to learn a new language, you want to learn how to program in Python, or you want to learn a new sport or a musical instrument. Clearly, when you start out, you're a different person than when you finish. Something changed in your mind, in your way of seeing things. Same thing with these neural networks. These weights are called trainable. They're trainable parameters, and they will change. So you start out typically by just randomly assigning them, and then as your network gets smarter and smarter and smarter, these trainable parameters will be modified with purpose to get to where they need to be. And we'll see how that process comes to being. So we've looked at the format and the modular representation of what happens with regards to these mathematical operations. What instructions do these graphs encode? And so you can see that here again can be represented in the form of matrix vector multiplication, and it tells the exact same story, right? This is a compact and a beautiful way to sort of say the exact same thing as we saw a couple of slides back here. Here we're using the summation sign, and you'll see these coefficients, and it's running across the weights, right? And then you pass that as argument into an activation function, which is represented here. Same thing, same story as here. What this says is for matrix vector multiplication is you take these x1, multiply that by w11, take x2, multiply that by w12, and take x3 and multiply that by w13. Sum all of that together, you get h1, which you then pass in as argument to sigma, and you get sigma of h1 here. And same thing goes for sigma of h2. So that's all that says. And in this talk, and really in any sort of deep learning endeavor, there are two prerequisites. One of them is two important prerequisites. The two most important prerequisites are linear algebra and calculus, differential calculus. And so those things are not they're typically not as difficult as they can sometimes be portrayed. So don't be intimidated by them, but just know that those are things that you definitely need to review and be comfortable with. Matrix multiplication, and the notion of what a basis is of a vector space like XYZ, and linear combinations and dot products and the like. That is the language of deep learning. And then even in this very talk, we're going to be using derivatives. We're going to be taking derivatives, which is, again, it's really is a simple concept. It's the notion of rise over run, of how fast a quantity is changing with respect to another quantity. So that's something that we use extensively in this talk. So that's I'm stating now that it's needed. It's a needed prerequisite. And so looking at this networks can be as complex as you want, right? Several layers deep, sometimes shallow, sometimes you could have a million layers. I mean, we're not in this talk going to talk about things like regularization and overfit and underfit and the like, which are some of the consequences of the extent of expressibility that you build into your network given the data, and there has to be certain matches and so on. But by and large, you have free reign to design your network as you please. And as I talked about, again, that modular mathematical operation can always be represented in a matrix very compactly as matrix vector multiplication, and you can work through this and see that how that works. And again, it's the exact same thing, as pointed out earlier. This is the networks can have all types of forms and shapes. This here is reminiscent of an autoencoder architecture in which there's essentially dimensionality reduction. You started out with 3, you ended up with 2, and then you proceed to increase that to 3 in this case. So that's sort of like it has that general shape of an autoencoder. But again, this is a repetition of our prior slides, and all that these things say are what we already discussed, is that the input nodes are each multiplied by the corresponding weight, summed up together, fed into the next layer, and then the activation function acts on that, and that then subsequently serves as input into the very next layer. And you can continue to multiply these things together in a very compact way, and you'll see how they wrap around. And this is essentially just another representation of the network in terms of its instruction set. All right. So the activation functions, that's an important part, right? That's a critical part of the process of training a network and specifying what that network is. And so again, once again, you see that here, the linear combination is fed in, and then that's transformed or so-called activated. And you have there's a range of options that a person has in terms of choosing activation functions. And one thing that you'll see is that the machine learning in general, deep learning in general, is a very heuristic field. It's something that trial and error, try it and see if it works. And it's not and that's part of why it's such a powerful field indeed. We're not limited by what we understand or don't. In effect, you kind of keep the car on the road, and that's how things have evolved. There are some phenomenological still points, such as the concept of vanishing and exploding gradients. And so here are some popular activation functions. So this one here is called the sigmoid function, right? And here it's 1 over 1 plus e to the minus z, where this is z. And you can see why it behaves the way it does. When z is large, e to the minus z is 0. So you're essentially looking at something that's essentially 1 over 1. And that's about 1 here. And it happens, and it stays right there. It asymptotically approaches 1, but for all intents, it looks like it's there. And then on the other end of the spectrum, as you go negative, e to the minus z, where z is a negative number, is a positive number. And so very quickly, this becomes enormously large. And so you have 1 over a very large number is 0. And it's right around the 0 that you see this transition occur. So that's the behavior of this particular sigmoid function. And it had some problems with it, okay? So as we will see shortly, and as I've already mentioned, gradient matters, like derivatives, matters and is an essential part of training a neural network. The process of training a neural network intricately involves and centrally involves taking derivatives. And as you've seen in the cascade, in that representation and in the network, the output of one layer is the input into the next. And you keep going like that. And so if, for whatever reason, something becomes an output or a set of outputs become very small, the effect and impact of those or very large, the effect and impact of that is propagated throughout the network. And so if it's to give you sort of recall that the activation function takes as its argument the linear combination from the preceding layer. Does that make sense? Let me just go back real quick. So yeah, this is activation function, and the thing that's inside it is the product and sum that came from the previous layer is thrown in there as the argument, right? So now that's the argument. So let's go here, and this is the argument on the z-axis. So if that argument is large, what happens? And what happens to the gradient of the activated output? The gradient is 0. So when you're backpropagating, and we're going to see what that means, backpropagation, you're attempting to take gradients of things that have gradient 0, and you're using that as a product to find other gradients. And so once you hit 0, you're pretty much stuck. Or when you hit infinity, it just blows up. So that's the concept of vanishing gradients and exploding gradients. And those are problems that one sees with the sigmoid type family of can see. Not all the time. It depends on the data set. As you'll see, it's everything in almost everything in deep learning is case by case. But that's a common problem that was resolved by the ReLU. In this case, ReLU type rectified linear family of functions don't have that problem, right? Because this one plateaus, while this plateaus, this one keeps going forever. And so you're not going to very quickly get to this zero gradient scenario. And historically, this was almost essentially some form of a breakthrough, but there's really been a constellation of factors that have kept machine learning moving forward and brought it out of its winter. In probably about a decade ago by now. Okay, so there's a plethora of examples of activation functions. All sorts of activation functions are out there. Take your pick. It really depends on the problem. Trial and error, see what works, and so on. And here's a nice list of all sorts of various ones that you can play around with. So now looking back at that, the neural network, I talked about a score function, a loss function, an objective function, a way to measure, a yardstick by which to measure how well you're doing. And that's going to be the guide, right? That's the essential grounding signal that decides and governs the training process. If you're off, then you have to get correct the issue, and if you're right, you have to be rewarded and carry on in that direction. And that's done by some form of really essentially similarity measure is an appropriate term, I think, always for a loss function. It's seen how similar is your network's approximation of the data. Your network was transforming this data into something, and how close did it get to the target, to where it needs to be, where you want it to be. And based on how close it is, that governs the training process. So here are some examples. Like an L1, for instance, you just take the difference and look at the absolute value of that, or you can square it and square it and take the square root. And then we also have categorical binary entropy, etc. We've in the fall we went into a lot more detail. Today, we're just going to have that in mind as a similarity measure that's going to guide our process. So the gradient. So now now that you have a loss function and you have your neural network, there's a process of training your network, in essence, and you have your loss. I said that we want the loss to go to zero during the course of training. That is the process of training. The whole objective, you can summarize the whole exercise of training the network as getting the loss to be small and as close to zero as possible, minimizing the loss. So looking at these representations, but you don't know exactly what the loss landscape is, right? You can measure the loss each time, and you want it to keep getting smaller, but you don't know, but you have options about what direction to go in. Because remember that the loss, we're going back to our representations of matrices and propagations. I'm going to skip back real quick here. Each of these things here that we talked about, right? You keep going through these, and essentially when you end in a loss function, the loss function is a function of everything that came before it. In particular, the loss function is a function of all of the weights inside of your network. That's critical. So your loss function is f of w, if you will. These are weights. This is your loss function. And the loss function is a function of all those things. And so when you want to minimize the loss, you have to take, you essentially would be needing to take the gradient of the loss with respect to the weights. And when you know what that is, then you can then use chain rule. And you can use the definition of the derivative then to correct that weight, to change that weight in the way that would decrease the loss or cause the loss to drop in the appropriate direction. So this is a representation of a loss, for instance, or a loss landscape. And if you think of Newton's method or Runge-Kutta, those are fancy words, but all that means is you're looking at slope, right? So if, assuming you're blindfolded and you're on a hill here and you want to know what direction to go in, all you have to find out is, how this thing is if you go this way, if altitude is going up and you go that way, altitude is going down, and you want to go down, then you have to go to the right. So at each point, you can think of the gradient as a sensor. The gradient is a sensor device at each point on this hill. So if you're blindfolded and you don't know which way is up or which way is down, but you do have a way of knowing what the gradient is, you're going to be fine. And that's exactly what we exploit, in gradient descent, which is the mechanism of learning, and learning here we said is the same thing as decreasing the loss. So you want to end up at 0. If this represents a map of the loss, you want to be here. You're here, you're blindfolded, you take a gradient, you see that the gradient is negative, that tells you go to the right. Okay? But how much to the right? So if I went like this, boom, I am no better than I was when I started out. In fact, if I go from here and I go like this, I'm here and it says go to the right and I go this much to the right, I end up here, worse off, right? So that's the concept of step size. And your step size has to be appropriate. If your step size is too small, then you're moving like this. Or step size, another term that's used for step size is learning rate. So you're moving like this, like this, like this, too little. You'll never get there. But then if you go like this, also, you're going to end up like that. So you just have to get it right. Another parameter, another heuristic that depends on the problem for which there's no mathematically closed form solution. And that's the name of the game, in deep learning, essentially. So the principle here is the gradient is a sensor, and the gradient tells you what direction to go in. What direction to go in so as to decrease the loss. And so that's what you do. And so it basically gives you these so-called weight updates. And so if the gradient here is negative, you'll move to the right. If you're here, gradient's positive, you'll move to the left. Eventually, playing that game, you would reach, hopefully, a global minimum, but there are also local minima, and it's beyond the scope of this, but there are multiple ways to escape local minima, from annealing to random restarts to various types of, again, heuristics, the name of the game. During the course of training your network, there's a stochastic, the gradient, during the course of the gradient descent, one could, on the one hand, if you have 1 million data points, take each single data point, and then based on the loss of that data point, make a change, right, to the weights, of all of the data. But that's going to take forever, to converge. Instead, what you do is you batch these things together. So you would have a set of 32 or 64, 128, and you would then run all of that batch, and then together then take the average, and based on the summation, the impact of the loss, like the aggregated loss, you would then use that as your loss function on each one of these batch, and use that value to make your updates. And so you'll get two things. On the one hand, you build in robustness into the system because you don't have this volatile system that's trying to make decisions based on single individual data points. You've added them up, so that builds in representation robustness, but also computational efficiency and speed, right? So you're enormously faster, and it's known that this works. It's not obvious that it would work, but it does. It works, and you do sort of a random walk, and you get to where you're going. So that's the stochastic part of gradient descent. So really, the meat of this is gradient descent in terms of understanding and in terms of principle. And then the stochastic, again, is a heuristic. I hate to use the word hack because it's more than that, but it's a way to speed things up and to be expedient with your computational technique. So here's a weight update, and this is this basically encodes the notion of a so-called this is the gradient. So this is how you would change the weight. So the weight, as I said, is the loss is a function of the weight, right? And it's a function of all the weights that are inside of your network. And so when you get to a particular node and you want to find out how the weight of that node affected the loss, you take the rate of change of the loss with respect to that particular node and you subtract it. And so that's a correction that would then fix, the impact of that on the loss. And so you use that, you replace WK with WK plus 1. This is a key equation in the training process. And this eta is your step size or your learning rate that I talked about previously here. And so do you go like this, boom, 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 or do you go like this, boom, 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 or like this? So that's again a parameter, a hyperparameter rather, that one has to that you have to play around with to get to the right place. All right. So the actual whole architecture of your network is, as I said, the loss is a function of everything in the network, because the loss is the final point, right? And these are all mathematical operations. So you can think of it as you did this, then that, then that, then that, then the other, and the other, and then you got the loss. And so we can apply the chain rule. The chain rule simply tells you how to take the derivative of a composite function. A composite function is a function of a function, like L of sigma of W. And so in this case, if you wanted to know how, and you remember W is embedded further in, right? Like W is a weight in layer number 154 of a 1,000-layer network. And you want to know how weight in layer number 154 affects the loss at the point 1,000, which is the final point in the output, so that you can then modify that weight so that it, in a way that results in a decrease of the loss, right? So chain rule tells you how to do that. So dl dw is simply, in this example, d sigma dw, that you'll take where sigma is an argument of loss. So you'll take the rate of change of the loss with respect to sigma and then multiply it by the derivative of the inside, the rate of change of sigma with respect to w. The sigmas cancel is a good way to see what's going on there, and you end up with this. So that's the chain rule. And your chain can be as long as you want. It can have 1,000 or 1 billion layer network, and still everything works out beautifully, because it's really on a modular step-by-step basis. How do we use that in training? And the way we exploit that is in a concept called backpropagation, which you might have heard about. This is a central concept within neural networks, within deep learning. And like a lot of the techniques, like we just talked about stochastic, the stochastic and stochastic gradient descent is really a device that allows for computational efficiency as well as algorithmic or data robustness. And so you'll see, because this is a very practical field and we're working with computers, that's the whole game. You can't do anything without the computer. And so a lot of even the mathematical methods that are utilized and the ways in which they're utilized are towards and for the purpose of allowing the computer do more with less, because essentially that means you can solve bigger problems. And bigger, of course, is a relative term, as always. So backprop. So what happens there? So you're looking at a network and you want to train the network. So the network has a forward pass, you get the loss, and then there has to be a backward pass to update those weights in the right way. And we've seen that the updates are guided by the derivative, the rate of change of the loss with respect to each individual weight. But that's not a trivial thing, a priori to compute. In hindsight, it is, because now we have backprop and so on. So the process, again, leverages the chain rule. And you can think of it as chain rule in reverse. So on the way forward, you store information in each of those nodes, because as you go, you compute gradients and keep those gradients right there. you will need them on the way back. So on the way back, you accrue an operand, which is a gradient up until that point. So in this case, what do I mean? In this case, you're coming all the way from layer number 1000, and hey, here's layer number 154. And you had the loss at layer number 1000, and you keep going backwards, backpropagating, accruing, accumulating. We'll see how. It's based on this, but this is happening at each of those nodal steps, and you're getting a value as you go. And so here, the output of layer 154 is F. As you're coming in, it turns out you're going to be coming in with this information in hand. And you'll see how. You're coming in with the rate of change of L with respect to F. As you leave, what you want to have is the rate of change of L with respect to W1. Well, you can get that information because what you would have done on the way forward is you would have stored the rate of change of F with respect to W1. This is W1 and that's F. So during your forward pass, which I indicate here by blue arrows, right, you have W1. When you get in here, you are able to compute F, the output, by what? We saw it earlier. It's simply by the activation of the linear combination of inputs multiplied by their respective weights. That's F. So you have F and you have W1 during forward pass. So what do? You take the rate of change of F with respect to W1. It's going to be a number. These are hard numbers, right? These are here, we're using symbols to represent them. But in a real world problem, remember I said all of your input data are numbers. So these are actual operations are being done. And so there you would then see the rate of change of F with respect to W1 is a number that you will store in this node. So on your way back, you would have another number that's the rate of change of L with respect to F. And all you'll then do to get this one, the rate of change of L with respect to W1, is multiply the rate of change of L with respect to F by the rate of change of F with respect to W1. So that's the brilliant beauty of backprop. It's an efficient algorithm that uses locality. It stores the local gradient on the forward pass, and then it accrues the gradient as it comes backwards in the backward pass. And then you do that back and forth, and that's how you train your network. So looking at it again, another representation of the exact same thing. It's so important that I'm just repeating it here in this next slide, the exact same story. This is a slide from CS231 course of Dr. Fei in Stanford, Fei Lee in Stanford, and Andre Karpathy from several years ago. I think around 2016, 2017. So here is here's the same story. So you're coming back with the rate of change of L with respect to some Z. Z is the output of this node here, this node F. It's almost unfortunate that this is called F because previously we had our output called F, but that's fine. So the output here is Z of this node F, and the input are Y and X. Y and X. So when we get Y and X, with Y and X and our activation function of choice, we're able to compute Z, right? So we have Z, and so during the course of our forward pass, while we're in this node, we have the quantities X, Y, and Z all in hand. So what do? Well, we go ahead and compute the local gradients, dz dx. We keep that number in this node, and we compute dz the y, and we keep that, knowing fully well that on our way back, for us to get the values dl dx and dl dy, we will need dz dx and dz dy, and just as shown in the previous slide. And then we simply take products. So computing a gradient is simply doing multiplication, and we're done. Beautiful. It's quite impressive, right? And And so here again is an illustration of that process. And you start out at the very end of the network. You start out with the loss function, and for the very last one, you have all the information. And it's a simple multiplication there. And so you then go backward and back and back and back, and at each step, you're computing what you need for the next one. And you have, because you started out here with full knowledge, you always have all the ingredients you need to cook a good gradient and the correct one. And so this is an illustration of the overall process of training the network. This is sort of a putting it all together slide. This slide here illustrates in the middle here with a neural network, and here's your network. We've seen representation of network. That's what this entire lecture has been about. There's a forward pass, which we've seen how that works. Right? We opened up with the idea of a linear combination that's then passed into an activation function and it's fed forward. That's called the forward pass. You just do all that mathematical operation until you get to a loss function. Then you hit the loss function. Now you have to then correct, because it gives you a grade, pass or fail. For speaking very simply, of course. And you have to make adjustments, as you go back. And so the adjustments that are made have to be appropriate to the node. It's like, how did you contribute to that performance? Was it good or bad? And so you have to then have the customized updates, weight updates. And to do that, you need the gradient, that particular weight at that particular node influenced the overall loss. And to do that, we use the backprop, and the weight updates happen. And then you just do that iteratively, and hopefully you walk very gracefully down this hill into a valley that hopefully is lush and beautiful with trees and birds and flowers and fruit and good stuff, not monsters and that type of stuff, right? So great. And then for homework at the end of this, there's more. There's always more. And to reiterate back to my opener, my starting point was that in whatever endeavor that you pursue, in this case, it's deep learning, it's AI, it's machine learning, it's that type of a thing. The key ingredient and the primary differentiator is almost always time and commitment. Like, how much time do you have for that? You might see your colleagues, your friends, going to PyCon, wearing the T-shirt, taking selfies, and put it on social media, and it's cool and having so much fun, and get them an internship and a job and all sorts of good things, But ultimately, no matter how much one would desire the same thing, the key thing is to say, look, I have to put the time aside. I have to set the time aside and sit down with this and just go at it. And when you just do that consistently, put in 2-3 hours or more. The more time you have, the better for whatever it is that you're looking at. And put in sometimes it takes years. It doesn't happen overnight. And then you'll just continue to grow. And you'll continue to make progress in the right direction, and before you know it, you'll be an expert. You'll be a serious expert, at this. But it can be hard. Parts of this can be confusing. You try to read a research paper, or even this lecture might not have made perfect sense to everybody, but that's completely fine. You just go back, look at everything that's available to you on YouTube, on the Medium, watch this lecture again, cross-check, look at different things. And there's homework. Here's our homework. And in our homework, which is the same homework that we did, or actually we did a class, we had this as a class exercise in the fall in Lagos, was we had a 5-hour lecture. So we had more time than this one. We basically build a neural network from scratch with no APIs, no Keras, no TensorFlow 2.0, nothing. Just write the code yourself, including backprop and stochastic gradient descent, and do it. You can do it for a simple 2-layer network, And that'll really force you to see what's going on. You can't really pull off that exercise without fully understanding backpropagation and stochastic gradient descent, etc. So that'll be the crowning example and the reward from all of this. I look forward to seeing all of you on Friday, 5 to 7, I believe, Nigeria time, Lagos time. And it's virtual. I'm going to be dialing in, and come with your questions. Also, you can hit me up already on social media between now and then. It's always a joy, always a pleasure to see you all. And thank you so much again. Thank you, Data Science Nigeria. And thank you, Dr. Bayo Adekambi. I'm always elevated by being a part of this community. Thank you.